Modern cognitive science relies on a specific assumption that memory and intelligence are generated within localized physical tissue. We study these intricate cross-sections of the brain because we believe the physical substrate is the absolute boundary of the mind. This paradigm extends directly into artificial intelligence. We rely on stochastic gradient descent to meticulously adjust localized weight matrices. In this view, a network's intelligence is the sum of those specific physical weights. But empirical data from biological morphogenesis and AI research shows that these localized models are surprisingly brittle. When the environment shifts, the intelligence shatters. These optimized models fail when presented with simple counterfactuals. A large language model can solve complex calculus in base 10, but fails basic addition if the prompt is moved to base 9. The model relies on narrow statistical patterns rather than a structural understanding of arithmetic. This recurring failure across both biology and silicon forces a reconsideration of the mechanism. We are left to investigate whether physical substrates are generators of intelligence or merely the receivers of it. Dr. Michael Levin proposes the thin client hypothesis as a rigorous alternative to strict physicalism. In this model, the brain functions similarly to a thin client terminal, a piece of hardware that accesses computational power from an external source. Levin identifies that external source as Platonic space. This is a latent layer of reality containing mathematical rules, symmetries, and structural regularities that exist independently of matter. Biological bodies and artificial architectures function as lenses tuned to ingress these latent rules. Matter doesn't invent behavior, it permits it. The configuration of the physical interface dictates which behaviors can be accessed. A specific neural architecture acts as a filter, limiting or expanding the range of cognitive competencies that can manifest in the physical world. If the thin client model holds, destroying the physical brain of an organism would not permanently erase its learned memory. The memory template exists externally, waiting for an interface capable of accessing it. The planarian flatworm is the perfect subject to test this. It possesses a centralized nervous system and a remarkable capacity for complete physical regeneration. In his operant conditioning experiments, Francis C. Ford used a Y maze and cocaine as a reinforcer to shape the flatworm's behavior. He successfully trained the worms to favor an arm of the maze they would normally avoid. The data shows a clear shift. Baseline entries into the active arms sat at 30%, but by the end of conditioning, the worms exhibited a statistically significant preference for the trained direction. Ford then decapitated the trained planarians, completely destroying their localized brains. Over a 2-week period, the tail fragments grew an entirely new central nervous system, a brain that had never experienced the Y maze or the reinforcement. Yet the regenerated organisms demonstrated a clear retention of the pre-bisection conditioning. They remembered a task they were never physically trained to perform. A newly generated brain exhibiting past adaptations challenges the assumption that memories are stored exclusively in localized synaptic connections. If the physical substrate was discarded and rebuilt, the information must have been stored elsewhere. This anomaly is not limited to biological tissue. We see the same pattern in artificial neural networks, where we assume deep learning is capturing the true structure of the world. Akarsh Kumar compared a standard multi-layer perceptron trained through SGD against a compositional pattern producing network, or CPPN, which is grown through open-ended evolutionary search. Both networks were trained to output an image of a skull. From the outside, the results were identical. Internally, the SGD network is a fractured web. The CPPN displays a clean hierarchy. Perturbing the SGD weights dissolves its output into noise, revealing no structural understanding. Shifting a CPPN node produces a semantic change, widening the jaw, aligning with underlying spatial rules. This reveals why LLMs can solve complex math, but fail on simple counterfactuals. They are memorizing patterns of data, rather than the underlying mathematical structures that generate that data. Because SGD optimizes for a single objective, it reaches a point solution, a fragile shortcut that collapses when the joints of nature are shifted even slightly. Why do biological evolution and open-ended AI succeed where top-down optimization fails? The answer lies in the specific way the system is built. The mechanism required for structural alignment is bottom-up complexification. Top-down optimization chips away at a specific target until it fits. Bottom-up complexification allows nodes to grow sequentially, with each new layer inheriting and building upon the properties of the one before it. In biological morphogenesis, there is no single fixed target. Evolving systems rely on generalizable rules that can be adapted to unpredictable environments. The pressure of surviving in a shifting world acts as a ruthless filter. Only adaptable architectures survive. This force requires a physical architecture to encode fundamental axes of variation, universal rules that remain stable even as the environment changes. Robust intelligence only emerges when an internal architecture is forced to mirror the mathematical symmetries of its environment. The decapitated planarian and the modular CPPN both suggest that physicalism alone cannot account for structural intelligence. In Levin's framework, causality flows from the top down. The abstract rules of mathematics and physics dictate what physical structures are possible. In this interface model, the physical substrate functions as a lens. It tunes itself to allow specific behavioral propensities to ingress from the Platonic space into the physical world. Intelligence, then, is the degree to which a physical interface aligns with these non-physical structural regularities. Biological bodies and artificial networks are tuning dials. When the planarian regenerates its brain, it rebuilds the specific interface required to access the memory pattern it previously aligned with. This suggests that scaling up current AI methods will eventually hit a ceiling. More data and larger top-down objectives cannot fix a fundamentally brittle architecture. Moving forward requires a pivot toward open-ended architectures that reward serendipitous adaptation over strict optimization. In medicine, treating cells as intelligence interfaces allows us to guide tissue repair through communication rather than trying to micromanage millions of chemical pathways. The flatworm, the neural network, and the human brain are all varied points on a single spectrum of physical interfaces. To build true artificial general intelligence, we must pivot away from memorization and toward the engineering of lenses capable of catching the underlying mathematics of reality.